How's it going, Jarek? It was a good weekend. Pretty relaxing, actually. Hope you all are doing alright, too. I'm trying something new out today. I have my tablet here set up to display the chat so I can just look forward and see the chat without looking off to the side or look up from the paper, I guess. But still have to look over and make sure my paper is centered properly, so I'm actually showing you what I'm writing rather than having it be off the screen. But it's something. It's something that I can do to improve things, I think. It also tells me we have 5 viewers currently. So welcome, everyone. I wonder if it tells me who those viewers are. No, it does not. Okay. Anyway, do hope everyone is doing well. What have y'all been up to in the other class? Still working on quadratic graphs, or have you moved past that? Yeah, that was last week's stuff. Mm-hmm. Let's see. Yeah, after quadratics is polynomials. I assume that's next. It's actually a pretty different topic compared to parabolas, because when you're graphing parabolas or graphing quadratics, I mean, you can find the x-intercepts pretty easy, and the vertex is relatively easy to find. We at least have a formula for that, which is nice. We don't exactly have the same luxury with polynomials. We can still find the zeros, and we find what's called the far left and far right behavior, because if you have a polynomial, I mean, it could very well look something like this, where it has 2 different zeros, where across two different points where it has x-intercepts, But at one of these x-intercepts, maybe the line goes across the axis here, and the other one it kind of touches it, but kind of bounces off. You know, depending on what's going on with the particular function, there's different things that you need to be able to do. Let's go into land. And then you have, does it continue up to the right or down to the right? Does it continue up to the left or down to the left? There's a lot of different things to take into account there. I don't exactly know how deep y'all are going to go into that. It looks like you're going pretty deep. Well, at least what we cover in college algebra, so it's largely similar because of that. There's a lot of the algebra type stuff we do in this class is basically the same as what we do in 13-14 class. I don't know if you've had 13-14 or if you're taking this as an alternative, but yeah, chapters 3 and 4 contain a lot of what we cover in a college algebra class. And chapter 2 for that matter, but yeah. No, I haven't given y'all any more homework, and it may be that we just have those 3, unless there's I think there's one more section I need to cover next week, which is section 1.5, so I'll probably give some more homework then. That way we'll have 4 total, and that's what I'll grade for this semester. I wish I had done it sooner, instead of trying to wait to try to to coordinate the assignments. I should have just did like I did back when, but it's okay. It's okay. Hopefully that was relatively easy homework, and hopefully an easy grade. I wonder the extent to which we'll actually need to solve these. Oh, I see. Yeah. So you'll be expected to do some factoring, but not like the really difficult stuff, from what I'm telling, or from what I'm seeing. For example, this is problem 20 on page 165. We're given f of x is x cubed minus 4x. A lot of the problems are factored for us already. 19 and 20 are not, but they're set up in a way that they are easily factorable. The first thing that we notice in both 19 and 20 is that there is a common factor of x. So x is our greatest common factor, and so we divide it out by taking x cubed divided by x, and negative 4x divided by x, leaving x squared minus 4 in parentheses. We can then go one step further and factor this quadratic equation we need two numbers that multiply to -4 and add to 0. What two numbers would those be? -2 and 2. So we can say f of x is equal to x times x plus 2 times x minus 2. Okay, and so that way we can factor the polynomial, and now we can do what we need to do to graph it. Okay. Let's see. I don't want to teach you more than you need to know, but I don't mind getting you started. See, they don't even talk about even and odd multiplicity, which I think is significant, because it lets us tell the difference between those two. Interesting. And it may be something that she brings up. So what I can do today is kind of introduce this section, because I've literally nothing else that I know I'm supposed to be doing. So I can introduce this section at least and give you some of the basics. That way she has a little bit better start on things tomorrow. Plus you can go in already knowing some or a lot about the material you'll be looking at, which is actually not bad either. Y'all said, I think y'all said she breaks you off into groups pretty frequently, or for a good amount of time. Y'all still do those breakout sessions, or whatever we call them. Anyway. Alright, so when we talk about polynomial functions, one of the things that we need to talk about is the leading term. So this is the term of the polynomial that has the highest exponent. And usually this is written first, that's why we call it the leading term. Although in some cases it won't be obvious what the leading term is because of the way the polynomial is written. It may be that, for example, our polynomial p of x is written x squared times x minus 3 squared times x plus 2. Okay. We've been given the factored form rather than the original polynomial, so it's up to us to figure out what the leading term is ourselves. Now, the leading term, when the polynomial is presented in factored form, as we see here, the leading term can be found by taking the leading term of each of the individual elements and then multiplying those together. Now, if our goal is just to find the leading term, we don't really have to multiply all of this together. That would be a pretty daunting task, I imagine. Not daunting, but tedious is maybe a better word for it. Some of you may find it daunting. But we would have to square this binomial, multiply by this other binomial, and then finally distribute this x squared. So it would take some time to get the leading term that way. But again, the goal is not to find the entire polynomial, we just want to know what the first term is. We just want to know what the leading term is. And so we know we have this x squared. Now if we were to multiply out x minus 3 squared, what would be the first term there? So we would take x minus 3 times x minus 3 and FOIL. How would we start that off? And again, we don't need the whole polynomial, we just want the very first term. Does anyone have that? Well, the easiest way to proceed is to take first term here, the x in the parentheses, and raise it to that power. Okay? So we take x and raise to that power of 2. So we know this one's going to start off x squared, and it's going to have some other stuff after it, but we don't really worry about that. Okay? And this is just x plus 2. So now what we do is we take the leading term of each of these parts, x squared, which is by itself, so technically a leading term, x squared, which is the leading term in the parentheses, and x, which is the leading term in these parentheses. And we want to put all three of those together. So basically we need to know what x squared times x is. So what would that multiply out to be? We just need to multiply these three things together. So x squared times x squared times x. The question is, how do we combine together those values? Close. It's not x to the 4. It's a little bit more than that. What exponent do we have on this x here? That's a 1. So if we're multiplying these terms, we actually add together their exponents. Yes, so it's x to the fifth. Now, again, we only want the leading term, the term in the polynomial that has the highest exponent. That's going to be x to the fifth. We took x squared. This term, x minus 3 squared, we know the first term would be x squared there. And then here the first term is x. So we took the first term from the individual parts and put them together to get our result. Okay. So we have x to the fifth power. That's our leading term. Now the leading term determines what happens to the graph at the far left as it continues to the far left and to the far right, beyond where our zeros are, basically. And it also determines how many turns the graph has potentially. So the leading term determines two things. One, the number of turns, the graph has at most. Okay. And two, where the graph goes as it continues to the far left and the far right, beyond the x-intercepts. Okay. So that's two different things that this leading term can tell us about this particular function. So we got a leading term of x to the fifth. Now, the 5, we sometimes call that the degree of the polynomial. The degree is basically the highest exponent that appears in the polynomial, so it's part of that leading term. Well, it turns out the maximum number of turns that a graph can have is one less than the degree. So a fifth degree polynomial could have up to 4 turns in the graph. Now, when we say 4 turns, what does that mean graphically? It means the graph, and again, we don't know what it looks like. It may do something like this. Okay, where it has 1, 2, 3, 4 turning points, where essentially the graph changes directions. So it's going up. Oops. Sorry. going up, it's going down, it's going up, it's going down, and it's going up again. So it changes direction 4 times. Now it may have that at most. There's no guarantee it will have 4 turns. It could have less than that, but not more than. Okay. Let me write that down a little bit more formally. So, not assume. Suppose our leading term is a times x to the nth power, where n is the degree and a is the coefficient. And that's the basic idea. So in this case, if we add 1x to the 5th, 5 is the degree and 1 is the coefficient. Okay. So 1, the maximum number of turning points is n minus 1. Sorry, n minus 1. Okay, second, and this is where it's a little bit more tricky. Okay. The far left and far right behavior can be expressed as follows. Make a table, and we need a little space here, unfortunately. There we go. Should probably, well, it's, what did the book do? Completely different than what I did, so it's okay. Not completely different, but different. They switched even and odd. So again, we set up here our leading term is ax to the n. Okay, a is the coefficient and n is the degree. We know the graph is n minus 1 turning points at most, at maximum. And then our far left and far right behavior can be expressed as follows. Now, what the book does, and I actually like what they've done here, is they've given an example of each of these. Like for this first one, we can think of it as f of x equals x squared, because it has a positive coefficient and it has an even exponent. Okay? If we think of that graph, we know that's a parabola that opens up to the left and up to the right. Okay? And so that's the behavior that's going to have as it continues to the far left and far right, is it's going to continue going up to infinity on the left hand side, and it'll continue going up to infinity on the right hand side. If a is negative, like we have a negative x squared, remember a negative in front of x squared takes the whole graph and flips it over so it reflects down. And so we'll actually have a negative x squared graph, which is a downward opening parabola. And so that goes down to the left and down to the right. Okay. So as it continues to the left, it continues down to negative infinity. As it continues to the right, it continues down to negative infinity. For an odd exponent but a positive coefficient, we can think of positive x cubed, which looks like this. Okay. Notice this goes down to the left and up to the right. So beyond its one x-intercept, it continues going down to negative infinity as it goes to the left, and up to positive infinity as it goes to the right. And then if we look at negative x cubed, that again flips the whole graph over. So it looks sort of like that. And so that one continues up to the left and down to the right. Okay. So this table, and there's a similar one in your book. It's got the first and the second line switched, but otherwise it's similar, and it shows the same type of graphs here, more or less. They use a little bit of variation here, but like for the x squared graphs, they put 2x squared and negative x squared, but essentially it's the same outcome. You know, the same outcome is that for a parabola, we know it goes up left and up right. A downward facing parabola, down left and down right. X cubed graph goes up right and down left, and negative x cubed flips it over so it goes up left and down right. And so that continues not just for these four graphs that we looked at, but any graph where we have an even or an odd exponent and a positive or a negative coefficient. So for instance, if we had put this over here for a second. Example, f of x equals negative 2x to the fourth. And again, we don't really care about the rest of the terms as far as the leading term is concerned, because that's our leading term right there. If the polynomial is written in the correct order, it should be written first, is basically what it amounts to. And so we like to put the highest exponent term first and then go in descending order from there. That's how we normally see it. But like I said, in the other example, it may be given to us as a factored expression where we have to figure it out ourselves. And that's where it can be a little bit tricky. Anyway, negative 2x to the fourth is our leading term, so that means degree equals equals 4, and the coefficient is negative 2. Now, first of all, focus, first of all, if we look at the degree, what are the maximum number of turning points possible? We had said maximum number of turning points is n minus 1, where n is the degree. So 3 turning points, yeah. Okay, so we have 3 turning points at maximum, or at most, whichever way we want to say that is fine. Doesn't mean it's guaranteed to have 3, but it won't have more than 3. And the second, what is the far left and the far right behavior if we have degree 4 and coefficient negative 2? Well, remember the two determining factors were that whether the degree was even or odd, and we have an even number, of course, and whether the coefficient is positive or negative, and we have a negative number. So let me show you our table again. If we have an even degree and a negative coefficient, which outcome do we end up with? Up or down, left or right? Down, which directions? Or which way? Down in both directions. Yeah, we have an even coefficient and a negative, an even exponent and a negative coefficient. So basically follow it down and across, and we arrive at this location. And so basically our graph is similar to negative x squared in that it continues down left and down right. Okay. Yeah, it's kind of the way we read this chart, and it takes a little getting used to, is we identify which outcome we have on the left hand side and on the top side, and then we see where those cross on the 4 outcomes here in the body of the table. And so in this case, because we have an even exponent and a negative coefficient, this is where we are. So down left and down right is our interpretation of that. Okay. That means whatever the intercepts are, and we don't know exactly what the graph will look like from here, because there's other things that we still need to figure out. Mainly we need to know what the x-intercepts are before we can really go much further. But if we have x-intercepts, it's fourth degree or fourth exponent. That means there should be 4 x-intercepts total. Some of them may be repeated, but let's say there's 4 unique x-intercepts. That means it will be down to the left and down to the right. As it continues beyond where our x-intercepts are. So notice it doesn't tell us what happens in between. So we don't know yet what happens in between these points. But we know there's 3 turning points at maximum, so it may be that it does something like this. Just using dotted lines, but then there's 1, 2, 3 turning points because it's going up, then it's down, up, and then down. So 3 different points where it changes direction. When you think of it as was it this? Did we talk about increasing and decreasing in this class? That was my algebra class. I'm sorry. I don't think we did that in this class, unless it's something you talked about it in the other course, the other part of this course. Yeah, that's just points where it changed directions. So we can say the graph is increasing, decreasing, increasing, decreasing. But 3 different times it changes direction. So it may look something like this, but all that we can determine from the leading term is that there's 3 turning points at most, which we've identified as possible here. In that it can, after it gets done with the intercepts, because we have 4x intercepts at most, it does continue down to the left and down to the right. Okay. It never comes back because there aren't any more intercepts over here, so it just keeps going down to negative infinity on this side and on this side. And that's what the leading term actually tells us. It won't tell us what happens in between. That's still to be determined, but at least we know what happens on the outside, on the left hand side, on the right hand side. Does that make sense? Anyway, it's a start to what you'll be talking about tomorrow, most likely with section 3.5. I wanted to go ahead and introduce some things there, just to give you an idea of some of the things, and then get you started on some of the things that you'll be talking about in that course, in that class tomorrow specifically. Now, as I said, there's other things going on in between. Now, the intercepts should be pretty easy to find, at least from what I'm seeing from the problems in this textbook, because in most questions the form and I'll show you what I mean in the homework here. In most of these problems, you can see, not those problems, sorry. I'm having a little trouble. Let me just move this real quick. And these problems, they want you to use a calculator for whatever reason, but I wouldn't worry about those. But like this 15 through 20 here, most of these are already factored for us. Okay. And then we talked about 20 and how we would go through and factor that ourselves, and then we can do something similar for 19 where we take out the common x and then factor the expression that remains. So we end up with 3 different binomials multiplied together. And so they're already factored for the most part, so we can easily find the intercepts, the zeros. Like for 16, it's x equals 5, x equals 1, and x equals negative 1. We just set each part of those equal to 0 and solve for x. Okay, which generally is the opposite of whatever number is there. 5, 1, and negative 1. So it's pretty easy to see what the intercepts are here, and what the book has you do is go through and pick some value in between those that tells us whether the graph is above or below the axis at that point, and helps us sketch the graph. But that is something you'll talk about more tomorrow, from what I understand. But the other thing we have to do is be able to find the leading term. And so like here, for 15, where we have x in the first parentheses, x in the second parentheses, and x in the third parentheses, we end up multiplying x times x times x. What's the leading term then? Well, it'll be x cubed, yeah, x to the 3. And so because the leading term is x cubed, then we know it has at most 2 turning points, one less than the degree. And with x cubed, we already know x cubed goes down left and up right. Okay. And so we know what happens on the outside, and we just have to determine what happens in between because of that. But what does happen, let me zoom back out there. What does happen, or what we can tell happens to a large extent, we said that x cubed looks like this. And that's really because it only has the one intercept right here. Okay. But if we had said something like x cubed minus 4x, for instance, we know that has a 0 here, then also at -2 and also at +2. And the graph will do something like this. It has the same leading term, so we know that it goes up right and down left, which it does here also. But with the extra term that follows, it has more going on in between. Or we could look at something like this, x cubed plus 2x squared minus, let's say 8x. It's actually very similar, even though it looks very different from this last one. The graph will be very similar. Let's see, that would be a -4, 0, and 2, but otherwise the shape of the graph is basically the same. Now what we do notice in this case is that because these intercepts are further away, we have a larger curve in between them than when the intercepts are closer together, like right here. Okay. Now, again, you don't really have to show this just by looking at it. You'll find a point in here to graph that helps out, I think, depending on how she shows you how to do this. But usually that's what we do. Anyway, but it's still, notice it still goes up right and down left, same as the other two graphs, but again, very different functions because this one is just one term, this one has a second term added, and these have 3 terms. So, but the leading term is identical in all 3 cases, so we know what happens on the far left and the far right is the same for all 3. The extra terms just change what happens in between. Okay. All right. Do you have any questions on any homework or anything else that you're working on? In this class, I mean, not necessarily other classes. This is actually probably a little bit easier than a lot of the things that we've done. I mean, this can be complicated, don't get me wrong, but it's very different than like the matrix stuff is always everyone's least favorite topic, I think. Um, but even the finance questions, those can get a little tricky as far as knowing which formula to use when, and then where do we plug in all the values to the formula, that kind of stuff. So compared to that, I think this is a little bit easier to do, but it does take some practice and understanding to get to that point. So anyway, um, I think that's all that we'll do today. I don't want to take away from what Mrs. Knisley's going to do tomorrow. You should have up to, but not including finals week. So let's see, this week, 2 more before Thanksgiving, and then the one after Thanksgiving. So 4 weeks. Well, technically, the Thanksgiving week is short, so 3 weeks and then half of another one. So, but on Thanksgiving week, they may still let you get 2 credits in if you need to. But yeah, I don't know. So technically 4, but it's more like 3.5 as far as the amount of class time we'll be able to meet. Wednesday before Thanksgiving, we're not going to have our class, so we'll just meet on Monday that week. Mm-hmm. Technically, we're supposed to go from 11 to 12 since the college closes at 12 and the day before Thanksgiving, but I mean, if we're only going to have half a class, why have any class at all? Especially with not a lot of work to do. We are ending most days by noon anyway, is the way it is. On the Wednesday before Thanksgiving, we're not going to have class, even though technically we are supposed to have class from 11 to 12. But, yeah. If you've been doing 2 hours a week since the beginning of school, you've probably already met the requirement or are very close, Geneva. Because what is this, the 11th week of school, 10th week of school that we're in now? May even be the 12th week. So you only need, what, 13 hours of credit? So you probably hit that back in October. And you can double check with your teacher, but yeah, probably you've already met that. There you go. Thank you, Caitlin. That doesn't mean you don't. That doesn't mean you can't go anymore. But I mean, if you feel like you need the help, definitely go get it. But at least you're no longer obligated to be there after 13. Mm-hmm. All right. So if there aren't any other questions, we'll go ahead and stop there. Hopefully that gets you all started for tomorrow's class, and when you see the first part again, maybe it won't be too strange. Hopefully I haven't led you astray and taught it differently than what she will do. Then I'll be upset that I did that. But I don't know how else you would teach this material. But anyway, not saying it's not possible. So we'll leave it there, and y'all have a good rest of the day, and we will talk again on Wednesday. Have a good one. Bye.